open circuit time constant method. We said previously that we can estimate the value of the 3 dB frequency or omega h by first finding the what's called the open circuit time constants, these taus. And the tau correspond to a capacitor. For each capacitor, we find the resistance seen by the capacitor when all the other capacitors are open circuited. That's why it's called open circuit time constant. And we set the independent sources to 0. So this way you find is a resistance seen by the capacitor. The time constant is the multiplication, C times R. We take the summation of all the taus, all the time constants. 1 over that would be the 3 dB frequency we are after. So this is omega h in the case I had 3 capacitors, CGS, CGD, and CL. We have 3 resistances for CGS, RGS, CGD, RGD, and for CL, RCL. And this is omega h in this case, 1 over CGS, RGS plus CGD, RGD plus CL, RCL. And this is an estimate of the gain function now. I know the low frequency gain minus GMR prime L. I can find it, if I don't know it, I can find it by doing the small signal analysis at low frequency and find VO over Vsig. And the circuit we have and the common source amplifier to be minus GMR prime L. And now we have an estimate for omega h. So the estimate for the gain now, the transfer function, the overall transfer function is AM over 1 plus S over omega h. And this is the expression that we derive for omega h. Let's do a numerical example. This is the same circuit that we have, the common source amplifier. And I have the following numerical values. The supply is 3 volt. I'm given K prime N and K prime P, W over L for all the MOSFETs, VTN and VTP, VAN and VAP. The reference current, 100 microamp. So this is, if you notice, this is the given that we had previously when we calculated the currents and we calculated the low frequency gain and output resistance. This is the same given, this is the same circuit. So we know from before what is the low frequency gain, what is output resistance, and of course input resistance here is infinite. So for now, I want to do a high frequency analysis. And for that, I need CGS, CGD, and CL for the MOSFETs. I'm assuming that the MOSFETs CGS, CGD are so small in femtofarads, which is the case for these micro electronic devices. Very, very small. Femto is 10 to the minus 15. So these would enter in the equations for the calculations that we would have to do to find omega h. And also our sig, which we really didn't need to know how much it was previously at low frequency, because the here the input resistance is infinite. So when you have an R sig and then after that the input resistance is infinite, I really don't care about the value of R sig because it's creating like a voltage divider with here an infinite input resistance. So it will have no effect. But now, when I'm doing high frequency analysis, I have the capacitor CGS and the capacitor CGD connected to this node here. CGD is like this, CGS is like from here to ground. So now I need to know how much R sig is, because this is no longer really an open circuit at high frequency. It's a capacitive input. So it's 50K. And we saw that it enters in all the equations that we derived when we derived the transfer function, or when we applied Miller's theorem, or when we did the OCTC. We had in the expressions R sig. Okay, so what are the questions here? Find FH, no surprises. We want FH, the 3 dB frequency, and FH, so that's in Hertz. Using Miller's approximation first. Okay, then OCTC, open circuit time constants, and then the transfer function, the exact omega h using the transfer function. All right. Previously, as I said, we found the small signal parameters and the low frequency gain and output resistance. So previously found GM for Q1, GM1 is 0.633 milliamp per volt. And what we are calling R prime L, which is RO1 parallel RO2, is 66.67K. So in Miller's approximation, what happens is that I would have the capacitors in the circuit, and then I apply Miller's approximation, and I end up with, instead of 3 capacitors with one of them bridging the input to the output, I will only have 2 capacitors, one at the input and one at the output. We call them C in and C out. And for C in, we will have a corresponding input pole frequency. So first we calculate the value of the Cn after applying the Miller formula. Cn, and this is something we derived previously, would be CGS plus CGD. And from the Miller formula, this is CGD, this here is actually CGD into 1 minus K. K Miller, the Miller multiplier, 1 minus K, and K in this case is minus GMR prime L. We said that we use the Miller theorem, but really with an approximation that the value of K, which is the voltage here, over divided by the voltage here, we can use the value of K, which we get at low frequency, which is minus GM R prime L. So 1 minus K is 1 plus GM, 1 R prime L. This multiplies CGD. And Cn would be therefore CGS 30 plus 1 plus GM R prime L. The gain for this amplifier at low frequency was minus 42.2. Again, previously calculated. So this is where the 43.2 comes from. It's 1 plus 42.2. And this multiplies CGD times 10, and we get 462 femtofarads. Notice that CGD, which is 10, now appears in the equation as 43.2 times that. It appears as 432 femtofarads. So the contribution of CGD to the input capacitance is very large. It's a very large component of the input capacitance and much larger than CGD. 432 from a capacitor, which is really just a 10 femto. It appears at the input as if it's 432 femto. This is called the Miller effect or the Miller multiplication. A small capacitor, a 10 femto capacitor, appearing as a capacitor which is 432 femto. And then the total would be 462 femtofarads. Fn, what is the resistance that corresponds to this frequency? Again, we calculated this previously, and after applying Miller's approximation, the input circuit and the output circuit become simple RC circuits. And at the input, the resistance that corresponds to Cn will be R prime sig, just R prime sig, which is R sig in this case. So if we calculate this with R sig 50K, Cn 462 femto, times 2 times pi 1 over, I get 6.89 megahertz. This is the input pole frequency. There is another one at the output. And at the output, the C out is Cn plus CGD into 1 minus 1 over K. This expression is 1 minus 1 over K from Miller's theorem. And K is minus GM R prime L. So I get CGD into 1 plus 1 over GM1 R prime L plus CL. And that's 10 into 1 plus 1 over 42.2. So at the output, the contribution of CGD is not really major because I'm multiplying by 1 plus 1 over the gain, which is a number close to 1. So CGD appears as CGD plus something, plus a small increment. And then I have CL, which is 50. So I get 60.24 femtofarad. So that's the output. That's the capacitance at the output node. And the output pole frequency F out would be 1 over 2 pi C out R prime L. And that's 39.6 megahertz with C out 60.24 femto and R prime L 66.67 kilo ohms. So this is the frequency at the input, and this is the frequency at the output. So after we applied the Miller approximation, I get a transfer function with 2 poles and no zeros. And these are the 2 pole frequencies. So one is around 7 and the other is around 40. So Fn is less than 4 times F out. Fn is 7 and the other one is 40. So there is a factor of maybe around 6 between them. So we can say that the input one is dominant and just estimate FH to be 6.89 megahertz. So this is the estimate we get if we apply Miller's theorem and then use the dominant pole approximation. So this is 2 approximations here, dominant pole and Miller approximation. And I will write this as FH being approximately equal to 6.89 megahertz. Or I can use the square root approximation if you want. And FH will be 1 over the square root of 1 over Fn squared, the first one, plus 1 over F out squared, the second one. So I get 6.8 instead of 6.9. And so this is what we get from Miller. Let's do now the OCTC. And in OCTC, I have my 3 capacitors. So again, this one, and now we don't apply Miller's theorem. So CGD stays and CL. And find the resistance seen by each of the three capacitors. But we already derived the expressions previously, so we can just use them. RGS for CGS is R prime sig, which is our sig here, 50K. RGD is this RXY formula that we want to learn how to use regularly. The resistance seen by this capacitor CGD, because it's bridging the input and the output connected this way. The resistance seen by CGD is R prime sig plus R prime L plus GM R prime sig R prime L, the RXY formula. And in this case, that's 50 times 43.2 plus 66.67. So that's 2,226.67 kilo ohms. So that's a large resistance seen by CGD. RCL is the resistance seen by CL, and it sees R prime L, which is RO1 parallel RO2, and that's 66.67 K. And now we multiply and add, multiply by the capacitor by the resistance seen by the capacitor, and then add all the time constants and take 1 over that. If I take 1 over tau, I get omega h. If I want FH, it will be 1 over 2 pi times tau. And OCTC estimates FH to be 5.87 megahertz. Okay, so Miller was 6.8, 6.7, maybe 6.8, 6.9. This is 5.9. What's the exact? Let's compare with the exact. If I go to the transfer function, the long expression for the transfer function, and I calculate exactly the poles and the zeros, where there is 1 0, the poles and the 0, I get, these are the exact pole and 0 locations. The first one is at 5.96 megahertz. The second one is at 386 megahertz for the poles. And there is a 0 at 10,000, 10.1 gigahertz. So this, the numbers here also confirm and verify what you said about the 0. It's at a very high frequency, 10,000 megahertz. And also the numbers show that FP1 is pretty dominant, is a very dominant frequency. It's around 6, and the next one is around 386. So that's a ratio of how much? 386 divided by 5.96, 65 times. So the next frequency is 65 times higher. And yeah, so FP1 is dominant. And I have an exact value for FP1. So I can say it's a very dominant pole, and then FH would be just that, 5.96. If I want to solve the quadratic equation to get the exact FH, I'll probably get 5.95 or 5.94. So that's the bandwidth, the value of FH from the exact transfer function. And we can say that this is how the body plot looks like. FH is 5.96 megahertz, and that's a 3 dB frequency. Where does this 32.5 number come from? Well, this is 42.2 in dB, 20 log 42.2. The low frequency gain is minus 42.2, so that's 20 log of absolute value of minus 42.2, 32.5. So let's now see how accurate were the estimates of Miller and OCTC. So if this is the exact the OCTC gave us a pretty close estimate, 5.87. So OCTC, the error in OCTC was minus 1.5%, which is pretty good. And the error in Miller, on the other hand, is large, kind of large, almost 14%. And that's, again, that's because we applied the Miller approximation, and that would give us this error. So these are typical values, actually. The OCTC will give a few percent, Miller will give a larger error. The nice thing about Miller is that it really simplifies the analysis. And you will see that we kind of like it, even though it has a larger error. OCTC is not bad, it's not too complicated. And but it involves more calculations, and it gives a smaller error. And of course, I can do much more calculations and find the exact values for the critical frequencies and the 3 dB frequency. So we always have these trade-offs between accuracy, error, and effort. Okay, now let's take the same amplifier we analyzed at low frequency and at high frequency and see if we cascade 3 stages of the same amplifier. So this is the amplifier we had. And we will redo the cascading analysis. Previously, the question was, what will be the overall low frequency gain if the per stage gain is minus 42? So this is a question we've seen before. Now I want to ask the second question. What would be the 3 dB frequency if the per stage 3 dB FH is 6 megahertz? So we just analyzed this one, and we got an FH of around 6 megahertz, approximately 5.96, so around 6 megahertz. So this is the same. It will have an FH of 6 megahertz. This is the same. It will have an FH of 6 megahertz. And the low frequency gain is minus 42.2. For the first question, we know the answer. We know that if we do this cascade and their MOSFETs, they don't load each other, the overall gain, so V out, the last output divided by the first input, V out over Vn would be minus 42 times, minus 42 times, minus 42. And we get a very large gain of more than 70,000. So this is what happens to gain. We multiply the individual gains when the stages don't load each other, and we get the gain at low frequency. What about the 3 dB frequency for the overall amplifier? So now I have, this is the final output. This is the initial input. I want the 3 dB frequency going from here to here. Each of these stages has a body plot like this. They drop at 6 megahertz. This one drops at 6, and this one drops at 6. So at what frequency would the gain V out over V in starts to drop? What is the 3 dB frequency for this? Is it the same as the individual frequencies? Is it larger? Is it 6 times 6 times 6? Is it 6 plus 6 plus 6? Is it 6? Is it smaller? Let's see. Okay, let's see. Let's analyze this mathematically and see what we get. For each of these stages, this is the gain per stage. This is the gain per stage, minus 42 or minus 42.2 for this one, for the first one, minus 42.2, but that's fine. 1 divided by 1 plus S over omega H for the stage, which is 2 pi times 6. And this is in megahertz. This is in mega. So I have 3 stages with a transfer function that looks like this per stage. If I want the transfer function overall, I will multiply the transfer function per stage. So first stage, second stage, third stage. And this will be the overall transfer function. Minus 42 to the power 3, the gain at low frequency, divided by 1 plus s over omega 0 to the power 3, because it appears 3 times. And then if I take this, replace s with j omega, I want to solve, when would this be? 43 to the power 3, 42 to the power 3 over root 2. This is the definition of 3 dB, of the new 3 dB overall. And we get this equation, which is not too bad. Actually, we can simplify it. So the 42 to the power 3 would cancel. And I need to solve now this equation. So I take the cubic root of the 2 sides, and I get 1 plus omega h over omega 0 squared is the cubic root of 2. And this will give me omega h in terms of omega 0 times this factor, which is around 0.5. So 0.51 omega 0. So the overall omega h, when I have 3 amplifiers with an omega 0, which with the same omega 0 for the 3, would be half. So the overall amplifier has a 3 dB frequency of 3 megahertz, not 6. So it's half. Can I get this without going through all these math formulas and details? Well, yeah, we can do this approximation. We can assume that the overall amplifier, the 3 stages, are like 3 poles in one amplifier at 6, 6, 6, and then use this square root approximation. And this would work if the 6s are different. So maybe 6, 5, and 4, or whatever numbers. So if I do this approximation, I get 1 over 6 squared plus 1 over 6 squared plus 1 over 6 squared. So 3 over omega 0 squared. 1 over that would give me 0.58 omega 0. So maybe not 3 megahertz, maybe 3.5 megahertz. And this is an approximation. But this will show you that when you cascade amplifiers like this, even though the gain increases a lot, you get much larger gain, but you lose in frequency, you lose in bandwidth. So the bandwidth would drop when the gain increases. And that's a typical trade-off that we see in amplifiers. If you want more gain, you'll have to live with less bandwidth. If you want less gain, if you're okay with less gain, you may get more bandwidth. So this is the gain bandwidth trade-off. In some kinds of amplifiers, this is almost a constant. So the gain bandwidth product is almost constant, which means that it's up to you to decide. If you want more gain, you will get less bandwidth, and if you want less gain, you can get more bandwidth, and the product is almost constant. So we'll return to this topic later. Okay, let's do another exercise with the BJT. This is a typical exercise we see. Given an amplifier circuit, find the 3 dB frequency FH using Miller's approximation, assuming also, so we want to use Miller's approximation, and we want to assume, we were asked to assume that the input circuit only determines the value of FH. Okay. And this circuit I have, when I analyzed the common source amplifier, we said that we can use the same equations if we have also common emitter. So the same equations would apply, and I can use them here. There is a difference that I don't assume R prime sig is R sig. So here R prime sig is R sig parallel with R pi 1. In the BJT, there is this R pi between the base and the emitter. This I don't have it in the case of the MOSFET, it's infinite. But if I have an R pi 1, then in the equation, when I use R prime sig, when I see R prime sig, it's not simply R sig, it's R sig parallel R pi 1. Okay, so I need to find FH using Miller's approximation and assuming that just the input circuit determines the value of FH. Let's go back and see what was this formula for the Miller approximation, and we will import it. Okay, where is it? Miller's approximation for CSCE. Okay, here it is. Next slide. Omega H is this. 1 over R prime sig. So this is Miller, assuming that just the input circuit determines omega H. This is what we need. And by the way, speaking of this course is open notes, open book. So all of these formulas, you'll have them. You just need to know where to look and what formula to use and when to use it, rather than memorize a formula. So you can search, but don't waste time searching. You will not have much time searching, but all the formulas are available, and you need to know what formula, where to find it, and how to apply it. So this is the formula that we need. Miller's approximation in CSCE with input circuit pole determining omega H. So this is 1 over R prime sig. R prime sig for the BJT is R sig parallel R pi. Into CGS, CGS becomes C pi in the case of BJT, plus CGD becomes C mu into 1 plus GM R prime L, and GM is GM for the BJT in this case. R prime L is RO1 parallel RO2. Okay, let's go back to our BJT exercise very quickly. Okay, and we are, oops, here. The Miller constant, K, in this case, is minus GM1 R prime L. Okay. R prime L is RO1 parallel RO2. Okay. We apply Miller's theorem to obtain the input capacitance. True. Cn is CGS plus 1 plus GM1 R prime L CGD. This is from the MOSFET analysis. And in this case, I don't have a CGS and a CGD. They're called C pi and C mu. So CGS becomes C pi. This was CGS, and this was CGD. And the BJT case, they're called C pi and C mu. And K is this minus GM R prime L. So this is now C pi plus 1 plus GM1 for Q1, R prime L times C mu, and R prime L is RO1 parallel RO2, same as the MOSFET case. The resistance at the input is R pi parallel R sig, and we know why, because this is R prime sig, and in the case of the BJT, there's R pi here. So when we do the analysis, we get we see our pi in parallel with our sig. And then the omega h would be due to the input circuit only. We're given that. So 1 over r prime sig, Cn, that's it. R prime sig is this. Cn is this. And if I want the frequency in hertz, I multiply by 2 pi. So 1 over 2 pi Cn r prime sig. So that's the 3 dB frequency in this case for this BJT amplifier.